Welcome to a short video, well, hopefully short, we'll see how it goes, video that introduces the topic of pressure. And in order to do well with this topic, you want to have a good foundation in what a mole is, how to do temperature conversions, volume conversions, and unit conversions just in general. We want to think about pressure as a force over a certain amount of area. And so when you think about your shoes, on this side of my slides, we have a really comfy running shoe. And you can see it's got lots of area. Let's make that red. Lots of area that your foot is in contact with the ground on. And whatever you weigh, that's your force that's down on your foot. If instead you were wearing this shoe over here, you can see little tiny area there, not a huge amount of area over here, and so we can see that the pressure on your foot in this type of shoe would be much greater than on this type of shoe, because you weigh the same regardless of what kind of shoes you're wearing. And in one case you have lots of area in the tennis shoe for your force to be bearing down on, and in the stiletto you only have a little tiny bit here and a little tiny bit here, so lots of pressure on your feet. From a chemistry perspective, pressure comes from molecules hitting the sides of the container that they're in. And so you can see these purple particles over here, and they're bouncing into the sides of the container and then bouncing back. And so the container is essentially feeling the force of all of these molecules hitting the sides of it. We don't actually care that the molecules are going to collide with each other, because as far as pressure is concerned, we're measuring the pressure on the container. So molecules can slam into each other, it doesn't really matter, or it doesn't impact our overall pressure. The more collisions there are with the particles and the size of the container, the higher the pressure is. So pressure is generally given in units of atmospheres, which are abbreviated ATM, or millimeters of mercury. And on this particular presentation, it wouldn't let me do lowercase m's. So generally you'll see millimeters of mercury as 2 lowercase m's, capital H, and then a lowercase g. You might also see it in PSI, which is pounds per square inch, or in torr. All of those are possible units. Now, in my introductory classes, I don't ask students to memorize these conversions. I would give them to you if you were taking an exam or some kind of assessment that asks you to convert from one type of pressure unit to another. And since you're familiar with how to do conversions, using these as conversions shouldn't be that difficult. So let's talk about temperature and pressure. And what we want to think about is, here we have this person who is wearing a costume, and they're wearing a water molecule costume. And so we can think about them as a molecule that's running. So it's a molecule that's in motion. And temperature is a measure of how fast molecules move. So if you have a really high temperature, then you have a really high pressure, because the faster the molecule is moving, the more they run into the sides of the container, right? This was our container, and we've got our particles, and they're running around and they're smacking the sides of the container. If we have a warmer temperature, they're moving faster, so there's more collisions. Temperature and pressure then are considered to be directly proportional. As temperature goes up, pressure goes up. If we look at temperature, excuse me, this is, whoopsie, that's a typo. It should be pressure and the number of moles. And what we find is that the more stuff you have, the more collisions you'll have with the sides of the container, and the pressure should go up. So if I have, in this container, I have 5 molecules and they're running around, and in this container I only have 1, which one should have the higher pressure? So it should be the one that has more particles, because more particles means more collisions with the container. More collisions with the container means a higher pressure. So the amount of stuff that you have, which we're going to call the number of moles, is directly proportional to the pressure of the container. As the moles goes up, the pressure also goes up. If we look at pressure and volume, we want to think about volume as the space that the molecule has to move around in. And if you make the space smaller, then the molecule is going to run into the sides of the container more and more. Kind of like these people in this room, where they've been all packed inside a really small room, and the sides of the room are now running into them. You can think about this too as, here's my container, here's one container, which has, we'll say, 3 particles in it, and here is a little tiny, tiny container with those same 3 particles. Which should have the higher pressure? Well, the smaller container. Same amount of particles, and I'm assuming here the same temperature. A much smaller space to move around in means more collisions with the sides of the container, and so more pressure. And that means as the volume goes down, the pressure goes up, and that means that volume and pressure are inversely proportional.